Assalamualaikum and hello everyone. Today we will be presenting our project on determining the vitamin C content in fruit juice using iodometric titration, a topic that combines important aspects of chemistry with practical applications in nutrition and health. The importance of vitamin C. Vitamin C, or ascorbic acid, is an essential nutrient for human health. It is crucial for collagen synthesis, prevents the common cold, and boosts our immunity. It can be found abundantly in fruits and vegetables such as oranges, strawberries, and bell peppers. Given its importance, accurately measuring vitamin C content in food products is critical. Nutritional labeling helps consumers make informed dietary choices, while quality control ensures that manufacturers maintain consistent product standards. Furthermore, health researchers analyze vitamin C levels in various foods to understand dietary intake patterns and their impact on health. To measure vitamin C content, we use a method known as iodometric titration. It is a widely utilized analytical technique in chemistry, particularly valuable for quantifying the amount of vitamin C in various samples, such as fruit juices. This method occurs in a redox reaction involving iodine to determine the concentration of reducing agents present in a solution. Here's roughly how it works. An excess amount of iodine is added to the sample containing vitamin C. The vitamin C reacts with the iodine, reducing it. The amount of iodine that remains unreacted is then titrated with a sodium thiosulfate solution until the endpoint is reached, which is indicated by a color change using a starch indicator. The objectives of this experiment is first to determine the concentration of vitamin C in fruit juice sample using iodometric titration technique, and second is to standardize iodine solution.
Under this theory part, I would like to explain the principle of iodometric titration. The oxidation of vitamin C occurs when free iodine molecules are present. To measure the amount of vitamin C in a sample, volumetric analysis frequently used in this reaction. This volumetric analysis involves a titration process, which is iodometric titration. The underlying idea behind this is that 1 mole of ascorbic acid combined with 1 mole of iodine in a stoichiometric reaction, which produces a chemical equation as shown below. In an iodometric titration, starch acts as an indicator to show the reaction's endpoint. A blue-black complex forms from the starch that has been added to the iodine solution, then reacts with the iodine. The titration endpoint is marked by the development of the blue-black color.
Here are the apparatus and chemical reagents that we use during the experiments. As for metallurgy, we have preparations of iodine solution. The mass of iodine molecules needed to prepare a 0.01 m solution in 100 ml is weight. The iodine molecules are dissolved in a small amount of distilled water in a beaker. A spatula of potassium iodide, which is Ki, is added to make the iodine more soluble. Then we have to dissolve iodine and transfer into a 100 ml volumetric flask. Next, distilled water and Ki are added to the remaining iodine in the beaker, and this solution is transferred into the volumetric flask. The solution is diluted to the mark with distilled water. So for the standardization of iodine solution, to standardize the iodine solution, 10 ml of sodium thiosulfate solution 0.0 m is pipetted into a 250 ml conical flask. The solution is diluted with approximately 100 ml of distilled water. The diluted sodium thiosulfate solution is titrated with the iodine solution using starch as an indicator, and then the color change from colorless to blue is observed. Next, we move to the preparations of orange juice. A 10 ml of orange juice is pipetted into a conical flask. A few drops of starch indicator is added to the diluted orange juice. And further determinations of ascorbic acid in orange juice, the 50 ml of burette is filled with iodine solution. The orange juice solution is pipetted and titrated with iodine solution. And the last one is the endpoint is recorded when the solution turns from colorless into blue color.
For the example of the result, we are trying to obtain two things which are standardizing the iodine solution and determining the ascorbic acid content in orange juice. Why do we need to do this procedure? First, standardization allows us to know the exact concentration of the iodine solution, which is essential for accurate calculation in the titration process. Next, determining the vitamin C content in orange juice provides important nutritional information. The volume of fruit juice sample used in the iodometric titration is 10 ml, solution of iodine used is 50 ml, and concentration of iodine is 0.01 m. Formula used for calculation is shown below. For the table 1, we need to calculate the ascorbic acid content in orange juice using iodometric titration. To calculate the volume of iodine used in titration, V final minus V initial, and we get 37.5 for trial 1, 27.9 for trial 2, and 41.7 for trial 3. Next, calculate the moles of iodine used by 1:1 ratio, meaning that moles of vitamin C equals to moles of iodine. Third, calculate the molarity of iodine solution, and we get 0.02, 0.03, and 0.015 respectively. Last, average milligram of ascorbic used is 1.151. To conclude, we need to find molarity of iodine to calculate the concentration of ascorbic acid used in the sample. For the table 2, the method of calculation for determining ascorbic acid content juice are the same like in table 1, and the average of ascorbic acid in 100 ml of juice that we obtain is 145 mg.
Now for the contribution of titration. First of all is clinical diagnostics. For blood analysis, in labs, titration measures different ions and compounds in blood samples. For antibody titration, it determines the concentration of antibodies in blood, which is crucial for immunological studies as well as treatments. Next up is the food and beverage industry. For quality assurance, titration checks the quality and consistency of the products. For example, measuring the acidity in vinegar or the salt content in food. Next up is nutrient analysis. It helps measure essential additives in food as well as essential nutrients. In conclusion, iodometric titration is a reliable and efficient as well as effective method for determining the vitamin C content in fruit juices. We presented examples of realistic titration applications in industry as well as titration methods. This technique utilizes the redox reaction between ascorbic acid and iodine, providing accurate and reproducible results with commonly available laboratory reagents. It is straightforward, cost-effective, as well as suitable for analyzing various fruit juices, aiding in quality control as well as nutritional analysis. By ensuring accurate measurements of vitamin C, this method supports both product quality as well as consumer health.